thank Emma once again and all of our speakers.
Talks remaining, 3 before the break and 2 after the break. And at the conclusion of the final talk, we will have some address from Bertrand and Davis. So I hope that everyone will be able to stay until this time. It is now my great pleasure to introduce the next speaker, Dr. Hyun Hang Hu. Dr. Hu is from Michigan Technological University, and before I get started introducing him, I would like to express my greatest thanks, and also from Gary Jacobs, for all of the help that we received from Yun to organize this session. Dr. Yun is the program chair in Energy and Fuels, and we are very grateful for this opportunity to have hosted the 3 full days of the symposium. I'd like to just quickly go and give a little background on Dr. Hyun's presentation. He's interested in including solar cells, photocatalysis, hydrogen storage materials, and the title of his presentation will be Catalytic Hydrogen Storage in Metallic Organic Frameworks via Hydrogen Spillover. His co-author is Faisal Cheng. Please help me welcome Professor Hyun. Thank you.
It's a great honor for me to give the talk to this honored symposium. Firstly, I would like to congratulate to the Roger David. Yeah, thank you very much. Yeah. And now I'm going to talk about the catalytic hydrogen storage. So we did the catalysis research for a long time, but since 2002, I shifted my major attention to this material related to energy. So we still keep some part, not the majority. So why I think about giving the talk to this owner session, actually I have to get some more the research related to catalysis. So this is I think hydrogen storage normally is not a related class, but this one is we use the catalysis to accelerate the hydrogen adsorption. So I would like to give this talk. The first one is we should discuss about is the energy issue. Actually, everybody here is the expert for the energy, so I don't need to say too much. As you know, the United States spend lots of on the petroleum. Actually, this is 900 million gallons of petroleum products every day. That's a big amount. But the United States doesn't have enough amount. Is actually the petroleum to afford this one. So that's why currently we are 50% is petroleum from out of the United States. We import from many countries. And there's 2/3 of petroleum actually we use for the transportation. So this is we consume the majority for this transportation. So transportation use the petroleum to make air pollution. So for example, 78% carbon monoxide, 45% is nitrogen oxide, and 20% of carbon dioxide from transportation. So that's related to this the petroleum. So if we would like to reduce the petroleum dependence, and also we reduce the air pollution, so we try to find the new fuel. So this is the current reality. And this is if we would like to find a new fuel, we pay attention to the hydrogen. For what reason, you can see here. So if currently we use the internal combustion engine for the car, and the fuel efficiency is not so high. That's actually is below the 20%. Normally it's below the 18%. So this is fuel efficiency is not high enough. And if we replace the internal combustion by the hydrogen fuel cell, then fuel efficiency can increase to the 60%. So this is the jump. And we can reduce the pollution because the hydrogen fuel cell got only one exhaust gas is water. So so if you use the hydrogen fuel cell to build the vehicles, then you can reduce the pollution and also increase the fuel efficiency. So that's very attractive. And if you would like to use the hydrogen fuel cell vehicles, you have to build this the hydrogen infrastructure. So if you buy the hydrogen fuel cell car, you need this hydrogen station. So if we do this one, so first we would like to build this hydrogen station, and also we would like to the storage technology to store enough hydrogen on the car for the 300 miles. So normally we need at least 300 miles filled one time. So DOE actually set us the target many times. First one they set the 60%, and then they changed it to the short-term and long-term. Now it's back to they said it's currently the 5.5% hydrogen storage, and the temperature is below the 30 to this 80 degrees C. So they said that the temperature and also the capacity is this current DOE target. So if you would like to develop a hydrogen fuel cell, actually currently the bottleneck is hydrogen storage. So we pay this special attention to this hydrogen storage technology. So you can see that there are 3 types of hydrogen storage technology, and we can use the high pressure to compress hydrogen into the tank. So that one is easy. We can see this every level use the high pressure, so hydrogen is used this way. So that's why it can give you the advantage easier to feed the hydrogen and also release hydrogen. But unfortunately, this one spends a larger space and also it's unsafe. You can imagine if your personal car is fully filled is the biggest tank of the hydrogen, and this you occupy this big space, and also it's feel uncomfortable. High pressure hydrogen is behind you, and any car accident, that should be the big problem. So that's one. The second one, we can use the liquid hydrogen. So we would like liquefy the hydrogen into the cylinder. Otherwise, we can easily to get a high capacity and also easily release and refill the hydrogen. But this is your gas transfer to the liquid. You spend a big amount of energy. Actually, 20% of hydrogen energy should be used to liquefy. So you lost 20% hydrogen energy. The secondly, that one is you have used the perfect insulate. Today there was not a heat exchanger with hydrogen, but this is impossible. So if you park your car in the garage, they always release the hydrogen and you feel the uncomfortable and dangerous. So that's the second issue. The third issue, we would like to use the solid material, absorb the hydrogen, let the hydrogen and sleep in your solid material. If you need it, just increase the temperature and decrease your pressure to wake up with the hydrogen, you get the hydrogen. So this is this is our idea, the idea of the approaches. But unfortunately, currently we don't have effective solid material to absorb enough hydrogen. So that's why it's current attention paid to this the hydrogen storage in the solid material. So this, if you can use the solid material, you can get enough hydrogen and also safe. Even use a car accident, they still sleep in the inside. So it's, for solid material, actually there's paid attention more than 50 years. And the first attention paid to what? Paid to metal hydride. There are many metals can react with hydrogen to form the metal hydride. So form the metal hydride, but it's very few metal hydride that can decompose back to the metal and hydrogen. So it's only the metal hydride can decompose back to the hydrogen, and the metal can use for the hydrogen storage. So it's the best one to pay attention to the magnesium hydride. So that one, theoretically, they can store the 7.65% of hydrogen. But theoretically, it's currently lower than this 5%. So advantage, another one advantage is low cost for this material. So it's low cost and high capacity, and this is the ideal material. But unfortunately, the reversible hydrogen capacity is smaller than 5% because this is due to the thermodynamic control. So thermodynamic limited, this one is difficult to decompose completely, partially. So actually, the first DOE set target is based on this one. DOE said you can see it's magnesium can theoretically store 7.65%. We said 6, and then we give it 1.65. This is the space. Actually, it's the average the almost 15 years. Nobody can reach this one. So that's why DOE is the change in the target. The second you can see is the sodium or aluminum complex hydrogen. That one is theoretically can store 7.4% hydrogen. Unfortunately, that material cannot decompose to the hydrogen. So, but in the 1996, and the research group they found is that if you dope in the titanium into this sodium aluminum hydride, and that one can decompose to the partially to release hydrogen. So since the 1996, the DOE put a big money would like to commercialize this one. But unfortunately, and they get a conclusion in the 2004. They said that one is not possible to commercialize based on the cost and the capacity. So there is, you can see another important examples and this attention paid is the carbon nanotube. In the 1997, one paper published in the Nature from this National Renewable Lab. They reported 5 to 10% of hydrogen can store at room temperature at the nanotube. So at that time, that paper is catching much attention actually worldwide. So many people put the attention to try to see that this is nanotube is a magic tube. They can absorb so much of the hydrogen at room temperature. But unfortunately, in the past 5 years, and there's the many independent level they conformed below the 1%. So 10% is due to the impurity, so the conformity of 1%. So this is three, actually is a well-studied material, actually is low ones can be commercialized. So there is in the 2002, and there are several new materials developed for the hydrogen storage. You can see here, the hydrogen hydride can use for the hydrogen storage. The reason is because of water, if you high pressure, low temperature, they can form the cage. And the captured hydrogen inside the cage. So you can see we need 200 megapart and minus 23 degrees C. Then you can form this hydrogen water and hydrogen water cage and the hydrogen captured inside. So the theoretical capacity can reach the 5.3%. So that's theoretically. And that paper is published in the Science in the 2003. And that one is, at that time, lots of people would like to follow this one. But now they give up. The reason is because kinetics is not so fast. And the capacity is only 5.3%. And low temperature, high pressure, that's not very attractive for the transportation. Stationary use is okay, but the transportation, you can say your car would like to keep the low temperature and high pressure. And if you feed this to your tank, you need a couple hours to stay there. So nobody like this case. Then another one is in 2002, there's not just the research group reported another one is lithium nitride. That one is lithium nitride can react with hydrogen to get a lithium or minor lithium hydride. So that one is not a new one. That one is was published in the 1910. This German scientists published it. But at that time, nobody paid attention to this reaction because at that time, hydrogen storage is not important. The second one is this one's lithium amide can easily to decompose to the ammonia, and this is the issue. Ammonia is poison for fuel cell. So that's one. The two reasons. One is hydrogen storage is not important in the 1910, and the second is a ammonia issue. But in 2002, we paid actually everybody paid attention to hydrogen storage. So it's one group actually is back to this research reported in 1910. They published this paper in the Nature. And most importantly, just like as German scientists said, the paper published in Nature, they didn't provide a scientific idea. Actually, the most important part, your attention brought back to the 1910. And before this paper published in the Nature, nobody paid attention to the lithium nitride. But this paper brought your attention to this one. So I say that's what here is new or older. I say this yes or no. If it's actually for hydrogen storage, it's new, but the principle is older. So that's like the review. The review for this Nature paper, they give the comments. They say the totally different. Some comments say that this is the very important. Some say this they're not provided the scientific, but the Nature published the paper. They would like brought attention to this material. So this paper is the most important contribution is this is low ammonia detector during dehydrogenation. So they said ammonia has a potential to give the ammonia, but they didn't detect ammonia. So in the 2003, we do the experiment to make sure why you didn't get the ammonia. The reason is because you formed the lithium hydride. Lithium hydride can capture ammonia, so you have no problem with ammonia. So after 2003, and there's many groups actually do the research in this area. So this is the two new material. And then this is the third one is the metal organic framework. That paper is the first paper published about hydrogen storage. The model is from the Yagis group. They published a paper in the 2003 in the Science. They reported the metal organic framework can store the hydrogen at low temperature. So you can see this material. That one is metal organic framework actually is the inorganic cluster linked by this organic ring. So they form the framework. Yellow one is empty area. If you see this one, so this is the material. It looks like ideal material. If you notice, if you use the absorption for hydrogen storage, you need a high surface area. And what is the ideal high surface area? That means all atoms of the material are surface atoms. That means always your solid material atoms can absorb the gas. What kind of this one? Actually, I think it's always think that this is a dream. You never reach it. Any material you have some bulk material, bulk atom, and the surface atom. But this one is all atoms is the surface atom. The reason is because they form the framework, and the space cannot hydrogen penetrate anywhere to touch any atoms. So it's Finnegan framework is ideal material for gas absorption. So that when this paper published, we are so excited for this areas because we think this is probably the only one material you can get is all atoms or surface atom. So they use this one, the material for hydrogen storage, and this is minus 198 degrees C. This is a liquid nitrogen temperature. They got this 4 to 7% hydrogen capacity. So this is very attractive. But unfortunately, at room temperature, only 1% of hydrogen can store it. So the reason is because hydrogen cannot touch any atoms. Unfortunately, hydrogen molecule has very weak induction with this material. So you can hold it. The weakness is they can escape at room temperature. Only at very low temperature, you can they must stay there. So that's the problem. Based on thermodynamic calculation, if you would like at room temperature to hold this hydrogen molecules on the surface, the interaction with the hydrogen must be reached or higher than the 15.1 kilojoule per mole. So interaction, the hydrogen and the solid, the surface must be higher, 15 or the kilojoule per mole. But the MOF and the hydrogen molecule interaction is only 4 to 10 kilojoule per mole. That's why the interaction not high enough. So this is hydrogen easier. The problem is you know, is that we need the hydrogen storage at room temperature, but this material need a very low temperature to keep the high capacity. So one way we would like to increase you have to increase interaction, hydrogen and the solid material. You can see we talk about this hydrogen and the MOF interaction. They here talk about the hydrogen molecule and the interaction with the MOF. So it's one way you can do is if you can dissociate the hydrogen molecule to the hydrogen atom. And the hydrogen atom is very active and they can have the strong interaction with the surface of a MOF. So that's one way. And as a catalyst guy, I think it's easy to think about is that for platinum, for the always transition metal, can easily dissociate the hydrogen molecule to the hydrogen atom. So this is for the hydrogenation the process we always use. But as the Lafayette groups, they use this one as catalyst concept to the hydrogen storage. They simply doping this platinum or the activated carbon, and they is mixed up with the MOF. They would like to use the hydrogen to dissociate to hydrogen atoms, and the hydrogen atoms diffuse from the platinum to this activated carbon, and they is diffused to the MOF. And this hydrogen atoms should has a strong interaction with your MOF, the whole hydrogen. So they did experiment. You can see that one is the MOF without this MOF5, without this the catalyst. You can see the capacity is lower, even is the 10 megapascals the hydrogen pressure. And if you combine this the platinum carbon and with the MOF5, you can see this hydrogen capacity is dropped to the 3%. So that's the basic. The idea is this one is hydrogen spillover. So it's dissociated at the platinum and the primary the spillover to the activated carbon, and then finally the slip to this to the MOF or surface. So that's the paper is from is the Lafayette group in the University of Michigan. So that's a breakthrough for this kind of material. So after this one, so now it's columnar pelletation. First one is we think about how come we just conform this is the results. Actually, it's so many groups impressed this one, but this is we should use a different independent lab to conform this result. So we actually performed the experiment by my lab to do this. Use the same conduction, same reaction, and as the reaction conditions, and as to repeat this one, we got us the same. So we up to the 5 megapascal pressure, we got almost the same results. The Lafayette used the 110 megapascal. We kind of my instrument cannot reach it too high, but it's in the same pressure we always get it almost the same as Lafayette. So that's conformed, and now there are several groups conform with these results. So we don't have any problem to repeat this results, but we currently most attention to pay this how is at room temperature the hydrogen so easily to diffuse from platinum to the active carbon and from active carbon to the MOF. So actually the atom's interaction with the carbon is very strong. And how can you at room temperature can very easily to diffuse to the surface? So that's the question. So firstly, we use the DFT calculation to show us how strong interaction between the atomic hydrogen and the MOF. So if you see this, we pay attention to this the active size of the MOF5. you can see there are 6 carbon atoms. Each one can actually get 1 hydrogen atoms. And also we have the oxygen, can also get this, the hydrogen absorption. So total we have 5 types of the hydrogen. So this is 1 here, and the 2 here, and the 3 here, and the 4 here, and the 5 here. So as we did calculation, we can see is for atoms for active size 1, they'll get the negative stability energy. So that means that the oxide is not active to absorb hydrogen, because if you hydrogen on this size, you will increase the energy. So that's one cannot hold high. All others, you can see the active 5 is here. This is also is very weak interactions. So because it's atomic hydrogen and this is active size. But another 3 is good. But size 4 is 43 is the kilojoule per mole. That's higher than the 15 kilojoule per mole we need. And for 2 and 3, with over 100 is the kilojoule per mole. So that's a stronger interaction. So first one we can say is some active size can strongly hold is the hydrogen. So that's a conformant. For this one, the most importantly, if we use the DFT calculation to show that this is, you have the chance to get this the hydrogen policy, you have to use the experimental conformant. The second thing you can say, if this one we just use the 1 atom of hydrogen to absorb it in this active size. So if you do calculation, you just use the 1 atom of hydrogen atoms to touch the 6 membrane. You break one carbon double bond, and you use only 1 electron to form the hydrogen and the carbon bond. Actually, so you use only 1. You have another electron you didn't use. This is the electron you didn't use. So it's, you can see this one, the energy is not, interaction is not very strong. But if you use this for here, if we use you can see here, if we use the 6 hydrogen to saturate the 6 membrane, and you can see that the interaction is stronger. The reason is because if you break 1 double bond, you need 2 hydrogens. So if you break the double bond, then you need 6 hydrogens. So you can see if you put all 6 hydrogen on, and even you get more than the stronger is the interactions. So that makes sense. So you can see the active size, they interact with the hydrogen can actually form the very stronger interaction, 269 the interaction energies. So this is two structures. One is armature and another one like a bird. So you can both use the 2 structures to get us high interactions. So that one, after we get this is the results, we think about it, that we have trouble. The reason is because so strong interaction, how can you let hydrogen move? So this is the first questions. And then after that, we would like to say this. Anyway, first one we would like to show if you hydrogen into your system, we would like to say if they have this carbon and hydrogen bond or not. We would like to use the in situ FTIR to do this one. So we bought us the FTIR instrument. That one can use for the up to the 100 atmosphere hydrogen. So we can use the high pressure and use the in situ to see we can form the hydrogen and the carbon bond or not. So before we make sure so we can get this hydrogen and the carbon bond, we have to know so if they form the hydrogen and the carbon bond, and where is the FTIR peak. So to this one, first one we use the DFT to calculation, we show you where is the carbon and hydrogen bond for the mouth. And then before we put the hydrogen in, we calculation, we just see in the between the 290 the wave number and to this 3,150 wave number, and there's very small is the FT is the absorption peak is between the 3,010 and the 3,150. In here, there's only one is very small peak. So it's, if you use the FTIRs without the hydrogen absorption, without the carbon and the hydrogen bond forming, you should consider only very small peak in this area. And then we do this, then we put the 2 hydrogen on this the 6 membrane. You can see this between this 290, 2,900, and this the 3,150. In this area, you can see the several strong interaction peak. And if you put a 4 hydrogen on, you can see this very strong peak is actually around the 3,000. So that's show you if you use the FTIR to trace monitor this area during the hydrogen absorption, then you can make sure if they can form the hydrogen carbon bond or not. So this one, then we do the experiment. You can see that this is the mouth without the catalyst. we didn't see the obvious peak in this area. So that means no hydrogen and the hydrogen atoms bond formed. And this one is, so this is the hydrogen absorption in the MOF 5 and, let me see, what's the difference between 5. Yeah, for this one is we use the MOF 5. We didn't use the hydrogen. We just used the catalyst, and then we put is here we put is the platinum aluminum the platinum activated carbon with the MOF 5, and you can see during the hydrogen absorption at the room temperature you can see the 290 to this 3050. In this is with number here you can see this biggest absorption peak. So we test this one is 5 hour, 10 hour, 15 hour. So we can see this, we really can see this hydrogen the carbon bond, and that's one. But after we do the exam, we would like to see the stronger interaction. If you see form the hydrogen and the carbon bond, that's a strong interaction. And how this bond can break. We would like to reverse hydrogen. That means you have at room temperature, the hydrogen and the carbon bond should be broken. So that way we do the desorption for the 10 hour, and we use the FDIR to detect again. Then here, there's always the peak on the FDIR, the absorption peak can disappear. So that means that one can form it, and also at room temperature it can disappear. So this is a reversible formula. So this is actually, this one is you can think about this. There's various changes because it's so strong the carbon and the hydrogen bond. How can they so easily form and break it? So now it's the more attention to the not conform that they can form or not. We pay attention to how can we expand this one is so unusual the results. Actually, as a catalyst the person, we always think about this. You need the temperature, but the other one is at low temperature you can break and form the catalyst. So we try to think about this one. How can we do? So far, there's 3 papers published from a theoretical group. They think about this. How can we can easily to break this hydrogen carbon bond? That means that your hydrogen can easily diffuse on the long term on the surface and at room temperature. So this is if this is a MOF is perfect, and the hydrogen if you diffuse on this surface, you need 120 to the 120 or is 150 kilojoule per mole as activation energy. So you need this temperature or is put some energy to overcome this energy balance. So that's actually anybody no trust this one. If you are perfect, your hydrogen should be fixed in this location, not as easy to move everywhere. So how can they do this? They did calculate this. If you see your format, if you have some electron hole, and then your activation energy can reduce by 50 kilojoule per mole. You have 50 kilojoule per mole, you have a chance to move at room temperature. So how can you get an electron hole? Actually, you can see for this is in organic cluster, that's zinc oxide. If the sum is per position, so you lost zinc, and then you can get electron hole. So when you synthesize this one, you can got lots of defect. That means some is the cluster is not perfect. They lost some zinc. If you lost zinc, they can actually form an electron hole. If you form an electron hole, and then you can get this, you can reduce your activation energy very much. Only 1/3 your energy activating energy you need. So if you do this one, it's okay, and then you can move. So this is the first one. They give the theoretical experiment why this can happen. So that is for the first explanation. The second, the paper published also give another explanation. They said they are not directed to get the MOF. They did a calculation for the nanotube. They say this: if the hydrogen atoms can open between the nanotube, that's beautiful. One nanotube is here. If you use over the hydrogen and the atoms, and there are another, the nanotube is another way, they can hop from one nanotube to another nanotube. The reason is here. You can see if this nanotube had, and there is a hydrogen atoms here, they form the hydrogen carbon bond here. And if you use another nanotube was close to this hydrogen, and they also can interact with this one. So at that time you are the two the nanotubes interact with this one. So at that time your hydrogen molecules from this the nanotube another time not completely break. this is half you interact with you and half with that one. If this is broken and they only partially broken, and they can easily move. So use this way, they said is your activation energy also is only 50 kilojoule per mole. So that was there are two way they said. And another explanation they said is the hydrogen atoms can form the physical absorption and the movement. That one I don't think that this is not easy because your atoms is so active, and we are also detect that this is chemical chemical bond. So I think that these two explanation is we can use the experiment for another one. Hydrogen physical atomic the hydrogen absorption is physical absorption and movement so easy. I think this is difficult. How can you hold it? They can easy to form the carbon bond. How can they form this weakness physical absorption? So that one is we think is we need more is the consent. So this is why I just borrow attention to the everybody's we are experimenting can show form the hydrogen and the carbon bond. And also calling this is two theoretical group give the explanation. And then when recently my group do this the calculation for this is kind of we found is actually if you are formed another hydrogen cluster, not as hydrogen atoms, they can the hydrogen atoms interaction with the hydrogen molecule, they can form the cluster. And then also can easily actually even they are activated and the energy is much lower than 50 kilojoule per mole. So that's makes it easy to move. The hydrogen atoms connect to your hydrogen atoms and then form the cluster. And the cluster they are longer, easily to touch another carbon. And then partially formed and then break and the partial form break. So the activity is low. So that's but today I didn't bring this as data. And so this is the cassette we are blocked here, and that's so it's. For this one, I would like to give a very simple conclusion. So you can see as if you use the platinum carbon catalyst, and it can remarkably increase the hydrogen capacity for the mouth at room temperature. That's for sure. And secondly is we use the FDI, in situ FDI, we detect is the formation of the carbon bond. The third one is diffusion means mechanism of atomic hydrogen on the mouth is not clear. We still need more experiment, more is theoretical model to confirm this one. So this is my conclusion, and this is we are got is the support from NS for Energy, DOE, and also is the national is the support and the American Chemical Society. So it's this I got a fund for the hydrogen storage, and that's all my students. I appreciate that they work hard. So we got lots of experiment, and that's the so this is the information I would like to share with you today, and welcome the question.
Oh, thank you. We have maybe time for one quick question. We're a little running behind time now.
Oh, sorry about that.
Yes.
Question. When you describe with your calculations the absorption of the hydrogen on the mouth on the carbon ring, I see that it looks like the ring goes from sp2 to sp3.
Yeah, exactly.
Is there any spectroscopy that can show you that that's what's happening?
We try to think about it, but it's unfortunately some peak there's the overlap with the origin is the mouth.
How about Raman?
Raman we didn't do Raman because we don't have the facility to do in situ. Otherwise you have to the high pressure to hold this one.
Right.
Yeah, you're right. Yes, if we can do the Raman, this is very good. But for the FTIR, sometimes you have to travel to get this the SPL3. Yeah, that's if you weaken your Raman, yeah, exactly. The end, yeah.
Right.
Any pressing questions? If not, please help me thank Dr. Hu one more time.